Okay, so next what I want to do is start handling the tidying up this this outliner here. So I want to move my elements into structure, into the structure hierarchy collection, I should say here. But more importantly, what I want to do is I want to start implementing this functionality whereby we're automatically merging these elements into a single mesh every time we generate 10 new elements, right? Or however many we pass in as the argument here into the main function. So this is really, you know, if you have a small structure, as I say, you don't need to do this, but as soon as you get into larger structures with more elements, this is it becomes essential from a performance point of view. So I'm bringing in a note here. So link objects, first of all, with the structure collection. Remember, we got a handle to that collection here. It was call. So I'll say call.objects.link. And what am I linking? I'm linking the element that I just created within the for loop here. So I'm linking the element. So it's going to take each of these elements and it's going to put it into the structure collection. Now, I want to get a handle to the very first element created, because if you think a little bit further down the line here, every time I essentially merge all of these things together, the single object that remains is going to have this name here, the name of the first one. And so I want to grab a handle to that particular element, because if you think about it, all these other guys are going to get merged into this guy. And so at the end of this code, the final single object that remains that actually has all of the elements merged into it is going to be this guy with this name, right? So it's going to be important for me to grab a handle to that object there. So what I'm going to do is I'm going to say if n equals 0. So if we're passing through this for loop for the very first time, and let me see, I should indent all of this because it needs to be within this for loop here. So if n is equal to 0, so the very first time we pass through this is only going to be one line of code, so I'll keep it on the same line as the if statement here just for space sake. So I'm going to say ob, I'm just defining a variable name here, ob to onLink is going to be equal to element. Okay, so that means that by the time I finish this code and I get to the very end and I've merged all of these things into this element here, right, I can then grab that particular element because it's going to be called ob to unlink or object to unlink. Okay, and we're only doing that if n is equal to 0, so on the first element created. So get a handle to the first element generated so that I can unlink it later. Now, what's that about? Well, I said that this line here is taking each element that just gets created and it's putting it into structure. It is doing that, but kind of annoyingly, it's not removing it from out here. So what it's essentially doing is it's linking all of these elements into this structure hierarchy here, but it's not unlinking them from the scene collection, the sort of master collection. And so you end up with them in two places. So you end up with the same element appearing here and then within this collection in here, which just makes for a really untidy outliner. And so that's why I want to grab a handle to that final element that we're left with so that I can unlink it from the scene collection, and so it only appears within the structure collection. It's all kind of not absolutely essential. It's just for me trying to keep my scene a little bit cleaner, a little bit tidier. Okay, so while we're thinking about sort of merging these elements, let's write the code that actually does it then. We'll come back in a few minutes and deal with the color, or assigning color. So what I want to do now is, you'll recall that I set this counter equal to 0 before I come into this for loop. So when I come into the for loop, I want to increment that counter by 1. So I'll just say plus equal to 1. So it goes up by 1. Now, if that counter has gotten all the way up to chunk size, which is just 10 in this case, well then I'm going to come in here and I'm going to merge all the elements, right? So what I'm going to say is if count is equal to chunk size, right? Or if n happens to be greater than length of edges minus chunk size. So this is just taking care of the fact that, let's say if chunk size is 10 and let's imagine there is 97 elements within our structure, well then the final 7 elements would never get merged in, because chunk size, we'd come in here when chunk size was equal to 90, but we'd never come in again when chunk size was equal to 100, because there's not 100 elements, there's only 97. So this additional bit of the condition here allows us to come in for those last 7 and merge those last 7 individual elements. So if we satisfy that condition, it means we want to take our elements and we want to merge them. Well, let's take care of some housekeeping first and reset our counter to 0. So it starts counting up for the next 10 elements. We'll write a function called, we'll call it now, we'll write it in a minute, combine elements, and let's do a print statement so that we can kind of keep track of what's happening. Very important for larger structures. So let's print an f string, the completed element, and we'll pass in n+1 for the element number, and then what we're saying here is we've completed element n of, and then this is the total number of elements. So imagine we've 97 elements, it'll go 1 of 97, 2 of 97, 3 of 97, etc. It's just feedback so that you can see in your console how your code is progressing if you're dealing with a particularly large structure. Now what we're going to do is update our 3D view. Okay, so remember that's dealing with this here. So redraw. So redraw is currently set to false. Now we want to come in here and say if redraw, right? So it's currently set to false, so we'd never come in and evaluate this. But is that a capital D or a lowercase d? It's a lowercase d here, right? So if redraw, if that happened to be true, well then we'd come in and execute the following code. The line of code is going to be this guy here. So bpy.ops.wn redraw timer, and then we're passing in type is draw win swap, and then iterations equal to 1. I'll be honest with you, this is the result of some Stack Overflow searching, because I was trying to work out how I could do this, and it turns out that this single line of code is the magical line that allows us to update the 3D view while your script is running, rather than waiting for the script to finish running and then updating the 3D view. It's probably not the most efficient way of doing things. That's why I've included a flag here that we can leave at false most of the time and only set to true if for some particular reason we want to see the 3D view updating as we progress. Alright, so now I should be able to, we'll leave that at false for now. Now I should be able to run this again, and instead of all of these elements down here, we should just see one element, which will be this guy here, and it'll be sitting inside of this collection. Right, so let's try that again. But before I do that, let me just delete all these. So I'm going to select this, shift select this, and delete. And I'll also delete that hierarchy as well. Alright, so now starting again. Let's run our code, and we're not going to see anything different over here in the 3D view. It's all over. The action is over here in the outliner. So let's try it. Of course, there's going to be some issue. Well, no great surprise. Of course, I haven't actually written the code to combine the elements yet, so I kind of jumped the gun there. We need to actually write. We need to write this function. We haven't written that yet. Let me just delete all of that. All right, so let's take that guy there. All right then. Okay, so we're going to join our elements and nodes into a single mesh. Now we're just dealing with elements currently, but we'll also write some code to build some nodes. Now, what I got to do here is I got to put a reference into the Stack Exchange page that I basically got this code from. And so if you want to sort of give credit where it's due, this is, if you follow this link, you will find the code that I'm just about to paste in. Okay, and I'll explain it best I can. So what we're doing here is we're cycling through each of the objects in our scene, and we only want to merge, because there could be many other different kinds of objects in our scene, but we only want to merge elements that have a name, right? Objects that have a name that start with element or that start with node. So if the object, cycling through each of the objects in our scene, if the object starts with element, if the name starts with element or starts with node, we're going to append that object into an empty list of objects, which we're defining it here. Okay, so there's your empty list, and then we're just appending things into that empty list. Okay, so the next thing we're going to do is we're going to come down and we're going to copy the context, right? And we're going to set that equal to CTX. Set the active object to be the very first object within this list of objects, okay? And then we're going to, because in order to merge objects together, you have to have multiple selected, but one of them has to be the active object. So we're basically here saying, right, well, let's make the active object the first object within our list of everything we have to merge. And let's then have all of the selected editable objects equal to all of the objects within that list. Okay, and then we're just calling bpy.ops.object.join ctx. So again, this is another one of those examples where I can't claim to have deciphered this all on my own. This is the reference that I'll provide you with if you want to do some more reading around the discussion associated with this particular solution. But the logic is actually not that difficult to follow. It's fairly straightforward. So we're merging everything into the first object, because the first object is the active object. Okay, now I should be able to run this hopefully, and we should end up with a single object within the structure collection. Let's try it. Okay, excellent. We're nearly there. So ignore this for a second. But within our structure collection, we have a single object, and that single object carries the name of the very first element. And of course, we just have one object in our 3D view over here, which we can go into edit mode on. All right, so we've done nearly everything we wanted to do. The last thing I need to do is unlink this, because I don't really want that reference to my object floating within the scene collection. I want to get rid of that, which means I want to unlink it from the scene collection. So that's actually very straightforward. It's a single line of code, and we can drop it in down here at the very end. Okay, so here it is, and it needs to be outside of our for loop. Okay, so outside of that for loop, we're going to call bpy.context.scene.collection.objects.unlink, and then we're passing in that handle to the very first object that we defined above, ob2unlink, which we defined here. Okay, so now let's delete all of that, and let's run this again. Okay, excellent. And you can see now, if I collapse that structure collection, we have nothing else in the scene, which means it makes it really easy for me to hide and bring back our generated structure, because it's all living. Well, it's only one object, but it's living within that structure collection. And you'll notice as well that it carries the name of the very first element that was generated, because we merged everything into that first element. All right, we're nearly there. Let's get on and generate some colors for this thing. Right, so within my for loop here, create a bit of space. I want to create a material, and I want to apply it to the current element. All right, so let's first of all extract the color information, color and force information for the current element. That's coming out of color, which we brought in. Where is it? Here, we brought it in at the very top. Okay, so there's our color. Where is it? There's our color. All right. Next, I want to determine or build a material name. That's going to be really important, because that's going to be the only way I have to identify what the axial force is in each of the members. I got to reference the material, or go and look at the material for the selected element. So that material must have the axial force magnitude in its name. So we'll just say emat underscore. We'll concatenate to that the element number, cast as a string, underscore, cast again as a string. We'll take the axial force. Remember, we stored the axial force as the last number in each row for each element. We'll divide it by 1,000, because we're reporting it in kilonewtons, and then we'll just tag on the end the units, kilonewtons. So that now means our material, the name of our material, is going to encode the magnitude of the force. All right, so we're going to now call a function which we have to write, which just generates our material. So we'll call the function make material. We'll pass it the material name. We will also pass it the or, G and B value, and we'll pass in 1 for the alpha value. And this is, I think, the roughness. What is that? The metallic value, essentially how metallic the thing looks, and then the roughness value. So this just governs the sort of look of the material. All right then. So provided we've got that material generated, the next thing to do is to set the material, or apply the material to the element. So we'll call another function, which we have to write, called set material. We'll pass in the element that just got generated, that guy up there, and we'll pass in the material. So let's just go and write these two functions now. They're pretty straightforward to write. So again, we're leaning on Blender's sort of boilerplate API code here, right? So make material takes in the name. Diffuse is just another name for color. The metallic value and the roughness value, both between 0 and 1. So we're going to say bpy.data.materials.new. We'll give it a name, the name we passed in. We'll set that equal to mat, just a handle to the material. And then we'll set the diffuse color, essentially the color, to whatever got passed in. That's an RGB value. we'll set the metallic value and the roughness value. There's a whole lot of additional things that you can set on a material, but this is going to be sufficient for us, and we'll just return the material out of the bottom. And then the next one we want is to set the material on the element, current element, and so we define a new function called set material. It takes in the object and the material, and let me see, we're saying ob.data. I don't know why I broke that up into two separate lines. Probably no need to do that. We're basically just saying ob.data.materials.append, and we're appending the material. So we're appending that material onto that object. Okay, and now we should be able to go over to our hierarchy, delete all this again, see delete hierarchy, and run this, and hopefully we'll get some colored elements where the colors are based on the axial force. Bingo, excellent. All right, just what we wanted. All right, we're nearly there. Last thing to do is just generate some nodes. So we've got some nice sort of what would we say? Spheres is the word I'm looking for. Some spheres on each node. So the logic here is going to follow pretty closely the logic for generating our elements. So we're going to come down outside of our for loop that we use to generate each of our elements. We're going to come in and we're going to generate our nodes, right? So I'll define a node material. The nodes can all have the exact same material. We don't need individual materials for each node. So we'll call our make material function again. We will give it a name. We'll just give it a value. That's just a gray value, and we'll set a metallic and a roughness value. They can be whatever you want. You can play around with those. Let's set up a for loop that cycles through each of our vertices this time. And I'm going to be pretty quick with this. I'm going to call a function that's to generate the node. Right, so let me see. Node, we've got to write that. Then we're going to link that node into our structure collection, okay, and then we're going to set the material on that node to be the material that we just specified, or that we just defined, and then we got to also add in the code that merges each of those nodes into our main object for our scene. So every chunk size iterations join all node objects. So exact same logic as above. We're calling combine elements, and then we're passing out a statement to the console so we can keep track of what's actually happening. All right, let me see what else. Okay, so yeah, we got to write this function, generate node. Okay, so I'm coming up here to below the function for generate element, and I'm going to come in and paste a function generate node, right? So I'm pasting it because it's all fairly straightforward. Generate node takes in v is the location, the x, y, and z location. Scale is that scale parameter that got passed into the main function call, which basically sets the size of the node. And then num going to be the number of the node, which is going to get used in the name when we name the node. So we're using the basic API code. So we're saying bpy.ops.mesh.primitive icosphere add. So we're adding an icosphere this time. We're setting the radius of the icosphere, the subdivision level to the lowest I can set it to, 1, because we don't need lots of detail on this thing. Enter edit mode false, align with the world, set the location to be the location that we passed in, the X, Y, and Z location. Then set the scale, set the shading to smooth. We're getting a handle to the object we just created, which we're going to call ico, and that then just allows us to set the name on that object. So ico.name is equal to the following string. So it's just going to be node with a space and then the number of the node as a string. And then we're returning ico out of the bottom of this. We're returning the object out of the bottom of this function. So that is the generate node function. And I think, dare I say it, that is it. We're done. Right, we're done, all bar the typos. So let's delete this again. All right, so here we are. Let's run this from top to bottom and see if it works. And it does. Brilliant. Okay, so there we have it. We've got an icosphere at each location, just a visual thing. You don't need it, but it kind of looks nice. And we have all our elements created. So we could, let me see, I'm going to delete those again. And let me change these up to 0.05. Now, I wonder if I set that to 2 and set that to true, what do we see? What does that look like? Okay, nice small structure. So the code runs through it no problem, but you can see it's building. And in fact, if I set that to 1, we're going to see we're going to have an update every time there's an element added. We can see it. Okay, brilliant. So you kind of get the idea of what that true and false does in terms of updating the viewport. Let's set that back to 10 and set that to false. So there you have it. The code's written. All you need to do now is model some nice structures, run them through the analysis Jupyter notebook, generate the color data, drop it onto your desktop, and then you can run this code and you can generate a nice visual of your structure with your axial loads indicated by the color. Of course, remember the other thing I said was if you don't want to see it on the structure in its original shape and you want to see the color, the structure colored in but on its deformed shape, all you got to do is, instead of importing vertices, import deflected vertices, that other CSV file that got generated when you ran your analysis code in your Jupyter notebook, and you'll basically see the deflected shape of your structure. And so that's exactly how this structure was generated. Okay, so it the code or the structure we based our code on was a pretty trivial little structure, but the exact same can be applied to much larger, more interesting structures. And so I leave that in your hands to see what you come up with. So I hope you found this helpful. It was just a nice little addition I felt was worthwhile making to the end of our space frame analysis course. And of course, the same type of thinking, the same kind of logic and sort of flow can be used to build other structural analysis data visualizations in Blender. The only limit really is your imagination in terms of what you want to do. We could build bending moment diagrams and shear force diagrams and all sorts of good stuff, because really all we're doing is we're adding primitives to our 3D scene and we're determining the parameters of those primitives, in this case color, based on structural data that comes out of our Jupyter notebook. And so you can take this concept, this idea, and run with it. And so there you have it. That's the end of it. I hope it was helpful, and I hope to see you on a Degree Tutors course at some point in the near future.